Welcome. In this video, we begin Chapter 7, Graphs and Trees. This is the beginning of Chapter 7, so we are in Section 7.1, Introduction to Graph Theory, and this is day 1 of 2. We'll look at graphs and models, and also terminology. Graphs and models. Here's a good question to start us off. Can you trace over each edge without lifting your pencil? This is a famous little problem called the envelope problem. See if you can do it. Give it a try. All right, let's see. Here is one way to do it. If I follow this pattern, so it looks like 3, 2, 1, 5, 4, 6, 5, 2, 4. There we go. Look at that. Piece of cake. In the 18th century, there was a real-life version of the envelope problem. In the city of Königsberg, which is now Kaliningrad in Russia, there was a river, and in this river, it split in various ways, as you can see pictured there. There were 7 bridges, and the people of Königsberg wondered, can you start at one location and cross over all the bridges exactly once and return to your original location? And it was an amusement of the day. People enjoyed talking with each other about this, but no one seemed to be able to do it. And so they started wondering, is there actually a logical reason why you can't do it? Or can you? Maybe we just haven't tried hard enough. And one thing we might do to start analyzing this problem is get rid of all the stuff that doesn't really matter. The map doesn't really matter. What is a little more abstract is the picture on the left. I basically have 4 land masses, A, B, C, D, and there are bridges that connect the land masses, and maybe with a picture like this, I can get a better grip on how to solve the problem, or if it even has a solution. Even more abstract, how about a picture like this? And this is what brings us to graph theory, where the only thing that really matters in graph theory are objects and relations. So in the picture to the right, I have 4 points, A, B, C, D, and they represent the 4 land masses, and they're related if I can get from one to the other via a bridge. And so the great mathematician Leonhard Euler, here's how you spell his name, E-U-L-E-R. It doesn't look like you'd pronounce it that way, but you do. His name is pronounced Euler. Euler looked at this problem. One of the residents of Königsberg brought it to him, and with this picture he laid the foundations for the whole area of mathematics we call graph theory. Euler did solve this problem, and we will talk about his solution shortly. Here is a graph. A graph is basically points and lines, or we really call them vertices or nodes, and what connects the vertices are edges. We can label the vertices of a graph so that I can talk about them more easily as I look at vertex A or consider vertex D. And I can also label the edges. So here we go, I've labeled them 1 through 10 in this case, so I can talk about edge 3 or edge 5. And there is a certain movement that takes place around a graph that we like to consider. So for example, a walk. A walk is a list, vertex, edge, dot, 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 and ending on a vertex, where the edges connect the vertices they fall between. Here's an example. I might write a list C5, D5, C, 6, E. And there we go. And it's really just vertex, edge, vertex, edge, vertex, edge, vertex. And that's a walk. I couldn't say something like C2, B, 5, F. You know, it's it does go vertex, edge, vertex, edge, vertex, but they're not connected in any way. Not a walk. When there are no multiple or parallel edges, we don't need to actually list the edges in our description of the walk. So parallel edges, multiple edges, that's when you have more than one edge connecting a pair of vertices. So like the 2 edges that connect C and E, this is an example of multiple edges there, or we might call them parallel edges. There are parallel edges connecting vertices D and F, for example. And finally, we say a walk is closed if the beginning vertex equals the ending vertex. So maybe, actually, if I just even stop it right at the beginning, how about that? There we go. There's a closed walk. A trail is a walk with no repeated edges, and a closed trail is called a circuit. Let's see, how about a trail? Something like C6E10F9D. There we go, let me draw that out. C6E10F9D. No edges are repeated, and so that is a trail. And if I continued it on, let's see, trail, and I included 5C, that makes this whole thing a circuit. Now, an Eulerian trail, or Eulerian circuit, is one that uses every edge in the entire graph, and that's the key for Eulerian. It uses every edge. Now, it turns out that the graph that's drawn here does not have an Eulerian circuit or an Eulerian trail. And you can maybe give it a try, see if you can convince yourself of that. But again, a little bit later, we'll talk about Euler's theorem on graphs and show why this is so. But there are many graphs that do have Euler circuits. In fact, this graph here is one that has an Euler circuit. You can try to find one, or here we go, I'll make one myself. So let's start at this vertex that I've put an arrow at, and let's just start. There we go, an Eulerian circuit. How about some examples here? Let's see if you can fill in the blank with the correct terminology. What goes where? See what you can do. All right. And this first one, this is a trail. Then the next one, a closed trail or a circuit. Edges 2 and 3 are called multiple or parallel edges. And this last big walk, this is a closed walk that is not a circuit. How about some more terminology? A loop, that is an edge that has the same vertex at each end. And so we have one example of a loop down there. The degree of a vertex, that's the number of ways to leave or enter the vertex. For example, look at vertex 2. So vertex 2, the number of ways I could say leave, if you were an ant on vertex 2, you could go in 1, 2, or 3 directions. So we say that the degree at 2 equals 3. Now look at vertex 4. Again, if you were an ant and you were at the point of vertex 4, you could leave in 1, 2, or 3 directions. So the degree of vertex 4 equals 3. So the degree isn't exactly the number of edges that connect to it. And the degree of 1, that's also 3. A simple graph is a graph with no loops or multiple edges. And a graph is connected if between every pair of vertices there is a walk. Every graph that we've seen so far has been connected, but here's an example of maybe a graph that is not connected. Maybe we are considering 6 people, and the graph represents who knows each other. So the graph isn't connected, but it's still one whole graph. How about this one? Let's take a look. So the DEG, that represents degree. And what are the degrees in the envelope graph? At 1, looks like it has degree 2. Vertex 2, degree 4. Vertex 3, degree 3. Vertex 4, degree 3. Vertex 5, degree 4. Vertex 6, degree 4 also. This is a simple graph. It has no loops or multiple edges. And how about the last 3 questions? Again, another terminology question. I encourage you, actually, pause the video and see if you can trace those walks and see what word is supposed to fill in the blank. All right, how about this first one? The walk, 1, 2, 3, 4, 6, 2, 5. So I'll trace that out on the graph. 1, 2, 3, 4, 6, 2, 5. All right, so that looks like a trail. It's okay that I repeated a vertex, that's fine. I just can't repeat any edges. How about this the second one, the walk 1, 2, 6, 5, 1. 1, 2, 6, 5, 1. That looks like a nice circuit. And this last one, 3, 2, 1, 5, 4, 6, 5, 2, 6, 3, 4. That looks like an Eulerian trail. So it's a trail because it began and ended at different points. Here's one for you to practice. Take a few minutes and see if you can answer the questions. All right, how about the solutions? Find the number of nodes and the number of edges. So the nodes, or vertices, there are 9 of those. The number of edges, that's 11, and I want to be careful about this. Some people think that what I've circled is a single edge, D through E to F, but it's not a single edge. It's actually 2 edges. I could have a single edge that goes D to F, but I'd have to draw it like that with no vertices on that edge. How about the degree of each node? Here we go. I'll label them. So I just brought those up in red. You can check your work there. And let's compare the sum of the degrees and the number of edges. Well, it turns out that the sum of the degrees is 22. The number of edges is 11. The sum of the degrees is twice the number of edges. Is that just a coincidence? It is not. Here's a theorem. In any graph, the sum of the degrees of the vertices is equal to twice the number of edges. Can you reason out why this must be so? Take a minute. Think about it. Can you do it? All right. Why is this so? Let's take a look at that previous graph. Here's how we might find the degree sum. I'm going to start marking edges around vertices and counting up so I get the total degree. I'll go alphabetically. So starting with A, 1, 2, 3, 4, 5. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So the sum of the degrees is 22. And as I've counted, I was marking edges, and how many marks does each edge get? You can see each edge is marked twice, right? Because when calculating the degree sum, I count each edge twice. Every edge has at its ends 2 different vertices. So you can see why this theorem has to be true. I'll conclude with a puzzle that is just for fun. Can you trace over each edge without lifting your pencil? In other words, is there an Eulerian circuit or an Eulerian trail? This is just kind of an amusing thing for you to try, but it also brings us back to the Königsberg bridge problem and Euler's work in graph theory. Give these things a try, think about these 2 problems. These are actually the 2 problems that we'll pick up with in the next video. All right, and I'll stop here.